So, it's 1588, and a young Galileo is looking for a job. And the job he wants is Professor of Mathematics at the University of Pisa. The people to impress, if you want that job, are the Florentine Academy, because it's the members of that academy who decide who gets the job. So, he's invited to give a couple of lectures at the academy, and what do you think he's going to talk about? This young mathematician, he wants a mathematics professorship. He talks about the shape and the size and the location of Dante's Inferno. So he talks about poetry, a great work of literature. And I'm going to share with you some of the things that Galileo talked about in these lectures and what he said about Dante's Inferno. And we'll look as well at how the questions raised may have influenced his later mathematical and scientific thinking. And this is a pathway in to looking a little bit more broadly at other examples of creative work in mathematics that crosses our modern ideas of subject boundaries, which I don't really like. And I'm going to argue that thinking across disciplines in this way is not only intellectually exciting, but academically vital. So the obvious question, then, is, for these lectures, which are perhaps the most important of Galileo's life so far, he's only 24, why does he talk about Dante? Why does he talk about poetry and literature? Exploring a fictional world like the Inferno seems perhaps more the purview of literature than of mathematics. But in fact, as a mathematician, I can say, exploring imaginary worlds is exactly what mathematicians love to do all day long. If you think about it, even though mathematics has millions and millions of real-world applications, in reality, there is no such thing as a circle, not a perfect mathematical circle, only approximations. There's no such thing as a perfect straight line that goes off to infinity in both directions. These are abstractions. They focus on the underlying ideas, and those help us to uncover the deeper truths. And this is actually exactly what literature does as well. In fiction, we create artificial situations that shed light on what people are going to do, how humans behave, the characters that we have, and help us to explore then human nature and human emotions. And once we're in a created world, whether that's set up with the axioms of Euclidean geometry or the text of Dante's Inferno, we are free then to explore it and play around and tease out the logical consequences of that setup. And if we're surprised that a mathematician is thinking about, knows about poetry, is interested in it, that's because we've fallen into the old false binary that somehow you can be either a numbers person or a words person. And in fact, the case is that for most of human history, mathematics is just another part of a broad cultural education. It's not in a little silo, only weirdos do mathematics. I mean, some of us are weirdos, but that's okay. There's weirdos everywhere. You don't do mathematics and then not be interested in anything else, and vice versa. In fact, poets did mathematics. Mathematicians wrote poetry. In a few centuries back in India, in the Sanskrit tradition, one would do mathematics and do it in the form of verse. Here is a lovely piece of algebra. Now, the word problems, you see on GCSE exams are not like this. It's like Jill gets 25 watermelons, and you think, why would... Anyway, I love this little problem. It comes from a book by Bhaskara, a mathematician about 900 years ago. The book is called Lilavati. That was his daughter. And he is teaching her mathematics by setting these lovely, lovely problems in the form of poems. And of course, nowadays looking at this, you could turn this into a quadratic equation, you could solve it, and that's all great. But I just really love the beginning of this. I love thinking about the square root of half a number of b's. It just really makes it fun and interesting. And there are these lovely poems that are doing mathematics. And so, if mathematicians are doing poetry and thinking about poetry and vice versa, then, of course, as mathematicians, we like to do mathematics in those contexts. So mathematicians have thought about poetry going back centuries. millennia. For example, Pingala, the Indian mathematician, in his Chanda Sutra, wanted to understand what the possible rhythmic patterns of poetry could be. And so by that I mean, in poetry and in language, we have natural rhythms of speech, and in poetry these are often codified. So of course we all know about iambic pentameter, things like this. That's the pattern of stressed and unstressed syllables in your poem, and various forms of poetry will have strictures on what kind of rhythms there are. So in English language poetry, we talk about iambic pentameters and things like this. And we might ask, well, what are the possibilities? In other words, how many feet, how many patterns are there that have a given number of syllables, let's say? So if you have 2 syllables, you can sort of write down what the possibilities are, and they all have names, actually. So the iamb is perhaps the most commonly occurring one that we're familiar with, and that's the dee-dum, kind of, oh soft, what light through yonder window breaks. That isn't obviously how you'd recite it if you were playing Shakespeare. And then you've got your trochee, which is the other way around. So, like, quoth the raven nevermore, right, stressed then unstressed. There are much less commonly used 2 unstressed syllables or 2 stressed syllables, and you wouldn't want to have a whole line of verse like this, but sometimes you get them alternating. So the poem Sea Fever by John Masefield, you've got the line, and a grey mist on the sea's face. So that's 2 unstressed, a Pyrrhic foot, and then a spondy, right? So those are 4 possibilities. And if we wanted to work out how many there are in general, and this is what Pingala did, not in the language I'm using, but this is what he did, then you can think, well, how could I get 3 syllables? We could take any one of those 4 possibilities for 2 syllables and add either an unstressed or a stressed syllable to make 3. So there'd be 4 with a unstressed one at the end, and another 4 with a stressed syllable at the end, so that would double it up to 8. And it just keeps doubling. Another way to think of it is if you've got, n syllables, each one, there's 2 choices, stressed or unstressed. So it'd be 2 to the power n if you're thinking mathematically. But this is the pattern you get, 2, 4, 8, 16, doubles and doubles. And in writing down the list of possibilities for the first few of these, we don't know exactly what symbols Pingala used because the original manuscripts are lost. But it would have involved using 2 symbols, one for the unstressed and one for the stressed syllable. So it's believed that this might be the first use of something like binary notation to list the possible patterns, rhythmic patterns in poetry, and you get the powers of 2. Now, in Sanskrit poetry, there's a different question we can ask, which brings in a different pattern. And that is that in that tradition, your unstressed syllables are called light syllables or lagu syllables. Your stressed syllables are called heavy syllables or guru syllables. And the convention is that the stressed heavy guru syllables last longer. They last twice as long. So you've got your lagu, light lagu lasts 1 beat, and your guru, the heavy ones, last 2 beats. And so then you can ask, not how many possibilities are there for a given number of syllables, but how many of a given duration, a given number of beats. And then you get a different answer started to come out because you're counting in a different way. Here's the first kind of 3 possibilities. So 1 beat, well, there's only 1 possibility, that lagu, that light syllable. If you've got 2 beats, you can either have 2 lagu, 2 short ones, or you can have 1 long guru. What about 3 beats? Well, you can have 3 short, light syllables, 3 lagu, or you can have a guru, then a lagu, or you can have lagu, then a guru. That makes 3. So, get our mathematical heads on, we've got a sequence there that begins 1, 2, 3. So the next number after 1, 2, 3 is, of course, 5. And that's where I've written them all down there. You can check my working if you don't believe me. So there's actually 5 possibilities of 4 syllables. And we don't need to write everything down forever and ever, luckily, because there's a way we can work this out. We can say, okay, if I now want 5 beats, now I could make that by taking a 4-beat expression and then adding 1 short lagu beat. So that gives me this collection of ones that end in a lagu. Or, if I want it to end in a guru, one that lasts 2 beats, then I could add a guru onto any one of the 3 beat expressions I already have. So the total answer then is 5 plus 3, which is 8. And in general, you can always do this. You can take the answer for like n beats long is you add the previous 2 terms of that sequence together. And you might recognize that as giving us exactly the sequence that starts like this, 1, 2, 3, 5, 8, the next one will be 13, 21, and so on. This is what we call nowadays, at least in this country, we call them the Fibonacci numbers. But those numbers arose in the study of poetry centuries before Fibonacci included a puzzle about this sequence in his book in about 1200. So this comes from thinking about poetry, these lovely mathematical ideas. And it goes the other way as well. So mathematicians draw inspiration from poetry and find interesting mathematics. But poets as well, if they're familiar with ideas from mathematics, they can refer to those and they use them as metaphors and symbols in their poetry. So because my daughter's in the hall today, Millie, she brought me this poem by John Donne, and she said, "Mum, you'd like this poem." When she was studying it, she'd come across it, and it's a valediction forbidding mourning, and he uses a metaphor of a compass. So he's saying, he's far away from his beloved, and he's saying we don't really have 2 souls, really we have 1 soul. But if we do have 2, he says, if our souls be 2, they are 2 so as stiff twin compasses are 2. So you imagine your compasses. Thy soul, the fixed foot, makes no show to move, but doth if the other do. So they're joined together, and though her soul sits in the centre, yet when the other far doth roam, it leans and hearkens after it, and grows erect as that comes home. Such will thou be to me, who must like the other foot obliquely run. Thy firmness makes my circle just, and makes me end where I begun. So it's this nice little metaphor, and of course, because it's John Donne, you get a few words like erect and things, but that's what he did. He's got this nice compass metaphor. A slightly more highfalutin compass metaphor is this one from Milton, very famously in Paradise Lost. He describes how God is creating the universe, and he has his golden compasses prepared in God's eternal store, and they circle around the vast profundity obscure. What a lovely thing. And this is God saying, this is the circumference. I'm creating this thing. And it's the metaphors of geometry and the tools, the mathematical tools of construction that are used. And I wanted to mention Milton because something else that happens in Paradise Lost is that he mentions a certain somebody 3 times. He mentions the moon, whose orb through optic glass the Tuscan artist views. Who's the Tuscan artist? He also talks about an astronomer who's looking at sunspots, and he mentions that person by name, and of course it's Galileo. This is a picture of their rumoured meeting. I don't think it's absolutely certain that they met, but this is sort of part of folklore that Milton actually met Galileo. So we've brought ourselves back, we've gone around the circle and brought ourselves back to Galileo. So let's think about what Galileo did in his lectures. So he's talking about Dante. He wants to impress the Florentine Academy. So it's good, if you're going to talk about any author, it's good to talk about Dante because he is the most celebrated and beloved son of Florence, and of course, great deal of civic pride around Dante. And what is he doing in these lectures? What does he want to do? He is not, and the audience is not, thinking that, this is genuinely, Inferno is genuinely a physically real place under the Earth's surface. He's not trying to prove that. What he's trying to do is to say, let's look at the work, what this great poet has envisaged. Is this something that is kind of consistent? Are the textual clues that there are? Could there be a world, could there be a space that has these dimensions, that fits everything together in a way that makes sense? So this beautiful equation, is there a solution to it? And if there is, that means even more kudos, to Dante who's given us this vision, this allegorical vision. And Galileo he presents this very modest demeanour. He presents what he's doing as a comparison between 2 earlier commentaries on Inferno and Here's a picture from one of those. So the first is by Antonio Manetti, who was about a century and a half earlier. And in this picture, you can see, so in Inferno, of course, Dante is guided by the poet Virgil through, they enter into hell somewhere on the Earth's surface. It's actually in Italy, somewhere near Naples, we're told. And then they descend together down and down through the famous 9 circles of hell, all the way down to the center of the earth, where Satan himself is entombed in ice. And as they travel, they meet all the kind of lots of different sinners and have lots of philosophical discussions. So this is what we're trying to understand then. What is this space like? What are its dimensions? So Manetti has got this commentary, and the other person he is talking about is Alessandro Valutello, came about half a century later, and you can see in pictures illustrating his work, you can see things like the diameter at this given point. So at each stage, Valutello would sort of reckon, how wide are we at this point? So Galileo's ostensibly comparing these two, but really he's adding in a lot of his own thinking and a lot of his own much more deep mathematical analysis to what's going on. So as an example, the first thing that he tries to do is to think about what's the basic shape of hell, the Inferno. So this is a picture from Manetti's commentary, and just to say, so Galileo agrees with him on some things. Manetti was from Florence, and Valutello was from not Florence, who cares where, Lucca. So if you're in front of the Florentine Academy, it's an amazing piece of good fortune that Galileo's analysis, almost always, if there's a point of disagreement between Manetti and Valutello, almost always Galileo finds that Manetti was correct and Valutello was an idiot. Doesn't say that, of course, out loud, but he almost does. So anyway, this is the basic picture, kind of cross-section that is the rough idea of the shape. So you've got kind of a cone cut out of the Earth. It's pretty big. So from one edge of it to the other, we go around 1/6 of the Earth's surface. It's centered on Jerusalem in the middle at the top there. So right above the deepest point, the apex of that cone is the center of the Earth. And then it's kind of 1/12 of the way around the Earth in each direction. So we sort of picture like a wedge with a 60-degree angle. And Galileo says, well, it might seem like then, what's the volume of this thing? Which no one else sort of managed to come up with a calculation of that. It's quite complicated. What's the volume of this thing? Well, it might look like it's a 1/6, if you're just looking at this as a slice, but it's more complicated than that, of course, because it's not even quite a cone. We might know the formula for a cone, the volume of a cone, but this isn't quite a cone because a cone would have a flat circular base, and this has got the ice cream scoop on the top of it. So it's a spherical cone, and the formula for that is, well, there isn't really a formula that's standard, but you can work it out, but it's not something that everyone just knows. Galileo, though, of course, he's a good mathematician. He's familiar with Archimedes. He knows what Archimedes did on the sphere and the cylinder and the cone. And although Archimedes doesn't explicitly give a formula for this shape or a way to work out its volume, you can deduce it, if you're a good mathematician, as Galileo was, from that work. And he did this, and he said, so the Inferno in volume is about 1/14 of the volume of the whole Earth. So that's the sort of first thing that he does that's going beyond in a quite complicated mathematical calculation. Incidentally, Valutello's version of hell, his model for it, would be a puny 1/1000th of this volume. So even Florentine hell is better than everyone else's. It's important to know. Okay, so Dante and Virgil are traveling down and down and down through these descending circles of worse and worse sinners. And this beautiful illustration by Botticelli shows us that it's not just as simple as, right, we've got 9 circles, let's just divide the space equally and slot them all in, done. Because there's different things going on in each of these places. There are cities, there are different kinds of punishments being done, there are different numbers of sinners at each level, all sorts of different things that are going on. For instance, at one point, so in the kind of the 8th circle of hell, so the people down there have done some pretty bad stuff, there's a subdivision there into 10 kind of smaller pits, or some English translations call them rotten pockets, but like pits. And so what are they all going to be like? Where are they going to be? How deep are they going to be? That's another kind of discussion. And we do get clues in the text. We're not just making guesses. We have a lot of little clues. Sometimes we actually get numbers. So at the 9th of the 10 of these torture pits, Virgil says to Dante, look around you. This circle, this hollow, goes 22 miles around. Now, if you're a mathematician, and you're thinking about circles, and you see the number 22, of course, you think of the very good approximation to pi that was essentially, that's what was used at this time by most people, 22 over 7. And before calculators, this is a really good and useful approximation. So if I see a 22 as a circumference, I, instantly say, what that means is 7 miles in diameter. So at that point, we know that the span of this space is now only 7 miles, so really close to the bottom. And so you get these kind of little mentions every so often. It gives you enough to go on to decide what this might look like. I encourage you to go and read these lectures. They're available online. They're fantastic. I will just mention my favorite bit of this puzzle. Here, right at the base of hell, at the center of the earth. The center of the earth is Satan's navel. He's buried up to his midriff in ice. He's entombed there. And in order to kind of get all the other things the other relative dimensions, you have to know how big that very last chamber is that contains Satan entombed in ice. And to know that, you have to know how big is Satan. How big is Lucifer? So there's this little verse, right, 34th canto, so we're nearly at the end of the book, about the emperor of the woeful kingdom, that's Satan, rose from the ice, and this is Dante talking, better with a giant, I compare Dante, than do the giants with those arms of his. So he's saying the comparison between, the ratio between me, Dante, and a giant is a closer comparison than that between a giant and just one arm of Lucifer. And then he gives us a maths puzzle, obviously, like all the best poems. Judge then what the whole must be. That is proportional to such a part. So fine, you work it out. So let's work it out, or let's follow what Galileo did. There's a missing piece here. We sort of know how big a man is, and we know the arm is about a third of the whole of your height, but we don't know how big a giant is. But luckily, elsewhere, it's very exciting, we get some help with that, because we meet a giant, earlier on, Canto 31, we meet a giant called Nimrod, and his face is as long and broad as is in Rome the pine cone at St. Peter's. And in other parts, just scale it up accordingly. Okay, so what's the pine cone at St. Peter's? I'm thinking of a pine cone of that big. No. Here is the pine cone at St. Peter's. It's a very large statue. It was there back then. It actually dates back to Roman times. It was part of the ornamentation of a temple. This is the pine cone. So we know that a giant's face is as big as that. And then this is what comes next. Galileo does. It's a brilliant kind of tour de force of boom, 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 boom calculations. Like, just imagine the audience sort of sitting there being dazzled by the speed of it. It's great fun. Okay, so let's do this. The measurement he's using is braccia, which, as the name suggests, means roughly an arm length. So it's difficult to pin down exactly what that is or was. Somewhere between 55 and 60 centimeters, or maybe 22, 23 inches, somewhere around then. But anyway, Dante is 3 of those, 3 braccia high. Okay, so that's the first bit of information. We know the pine cone, it's 5.5 braccia high, which I'm sure you all eyeballed that and could tell. So that's 1/8 of a giant, because a giant's, a human, your face from top to bottom is about 1/8 of your total height. So that's 1/8 of a giant, so we therefore instantly know a giant is 44 braccia high. Brilliant. Now we've got this ratio. We know that Dante, compared to a giant, is a closer comparison than a giant compared to the arm of Lucifer. And that gives us this inequality. Arm over giant, bigger than giant over Dante. This is not at all surreal. You're not having a strange fever dream. This is happening. So we can put all this information in, right? We know the giant is 44, and we want to work out the arm. We know Dante is 3, so we get this calculation, which rounding to the nearest 5, you get 645. That's the arm of Lucifer, and we know that the whole body is 3 times your arm, and so we get that Lucifer is at least, he's bigger than this number, 1,935 braccia. And so Galileo says, well, he's bigger than that, so let's kind of take a big round number that's bigger than that. He is 2,000 braccia high. And if you want that in pine cones, which I know you do, 365. So if that's, yeah. Thank you, Galileo, for that. So that's, an important piece of scientific knowledge that you now know, thanks to Gresham College. Well done. And we're spreading the new knowledge widely. So this is about 3/4 of a mile. So it's just a wonderful, and I really, reading these things, you really feel Galileo's having fun with this. But he's entertaining his audience as well. He did get the job, so that's good. That mission accomplished. There is one little riddle, though, which, before we move on to thinking about some other links between mathematics and other arts, I'll share with you. It's to do with the dome. Hell is this spherical cone, and kind of on the top of it, covering it over, is a bit of the Earth's crust, right? Actually quite a big bit, 1/6 of the way around the Earth. And, domes are kind of tricky things, especially at that time. Surely, says Galileo, isn't this just going to collapse in on itself? That's a bit of a problem. So what he does then is he says, I can picture him, he's in Florence. He just sort of make a knowing look in the direction just not very far away to the fabulous dome of Florence Cathedral, which was kind of a marvel of architecture of the time, designed by Filippo Brunelleschi, another huge source of civic pride, So you've got Dante, you've got the dome of Florence Cathedral, and he says, so, would this dome collapse in on itself? And he says, well, here in Florence, we don't have to worry about that sort of thing. We know a dome of 30 braccia wide can be as little as 4 braccia thick, or even 1 or maybe a half. So it's absolutely fine. We can just scale it up, job done, everything's marvelous. Now, there is a slight problem with this. The slight problem is we now know scaling, when you're scaling like physical objects like buildings or bodies or anything like this, it doesn't quite work like that. That's the reason why you can make a model of a building out of cardboard, but you can't make the building itself out of cardboard. So does Galileo, does he know this? Well, the laws that describe how scaling works, in particular the key one is called the square cube law. I know that before Galileo died, at some point in his life, he did know about the square cube law. I know that because here's a picture of the person who discovered the square cube law. It's Galileo. So, but maybe a bit later, right? So this is the riddle. We know Galileo in a book many years later, maybe 30 years later, called Two New Sciences. He explained about scaling, and he was talking about things like why animals aren't just, big animals are not just scaled up versions of smaller animals. The reason is, so their bones, for example, can't just be scaled up. The reason is the square cube law, which says when you scale up something like a bone, its volume will scale with the cube of the scaling factor, and so its mass will. But things like the cross-sectional area will only scale with the square of the scaling factor. So if you just sort of multiply every dimension of an animal by 10, its volume is 1,000 times as much, but its cross-sectional area sliced through bones or something will only be 100 times as much. So there's 10 times as much pressure on its bones, and that's going to be a problem. So that I'm showing you there, sort of scaled to look like they're the same size, but they're not. That's a bone from a mouse, a femur of a mouse and a femur of an elephant. And you can see proportionately the elephant is much thicker. It has to be because of the square cube law, and this is what Galileo explained in this later work of his. So the question is, when did he find that out? Did he know when he was talking about domes? Was it a knowing wink to the mathematicians in the audience? Look, we all know this isn't legit. We know domes are always falling down, but hey, amongst friends, little wink. Was it that, or was it that he genuinely didn't know? And in which case, when did he realize this? And was it thinking about this kind of question about giants and about domes in the underworld? Was it thinking about that made him start wondering about scaling? I like to think it was. So I think maybe there's a case that one of the key results and pieces of mathematics around how we scale things and how we build things, I think that may have come from Galileo thinking about this imagined world in poetry. So that's really cool. And to celebrate that and those positive consequences for Galileo and all of us, I want to spend the rest of this talk showing you just a handful of examples from other arts of the spur to creativity that we get when we cross over these alleged disciplinary boundaries. Because I think these things all blur into each other, and it's really stimulating intellectually to think about art and about music and about literature, and that gives us ideas in our own discipline and vice versa. So we'll start with art. I'll give you two examples from art. The first one will stay in Florence, actually, because Filippo Brunelleschi, as well as designing the Dome of Florence Cathedral, was also the first to work out and describe the laws of linear perspective. And that allowed artists like Veneziano here to produce, really for the first time, incredibly realistic but imagined architectural backdrops for their paintings. And it gives this wonderful, powerful resonance and realism to the imagery that they want to represent. And it's all geometry. Perspective, it's all geometry. There are geometric rules and there are geometric constructions that govern these rules, and it's mathematics that can prove to us that the rules really are the correct ones. So in this picture, this is the Annunciation. You've got the angel coming to tell Mary that she's going to have a baby who will be the Son of God. The perspective is perfect in it. So you can see that one of the rules of perspective is that parallel lines that are not parallel to the picture plane, any set of parallel lines their images will all meet at a point called the vanishing point. So if you look at the front to back edges of the floor tiles and then various other lines in the picture that are parallel to that, we can extend them all, and we find that they meet at a vanishing point. And this vanishing point has been chosen by the artist to give an extra bit of symbolism in this picture. And that's another thing you can do when you understand the mathematical rules. You can decide what you want them to do for you. And in this case, add more symbolism and meaning to the picture. So what's the symbolism here? Well, if you look at where all those lines are pointing to, they draw your eye towards this locked gate at the back of the scene. It's a locked gate leading to a hidden garden. That is a metaphor often used at that time. It's a symbol for Mary's virginity. So it's an extra layer of meaning in that picture that is made possible by knowing and applying these rules. And when the rules of perspective were first discovered, the word started to spread, and one of the key spurs to that was a book by Leon Battista Alberti called Della Pittura, that's Italian, not Latin. That's crucial because it meant people who didn't read Latin could still access this information. And he says at the beginning, he thanks Brunelleschi, but he says, look, this stuff is mathematics, and I'm going to say what the mathematics is. And then he gives geometric constructions of things like drawing a tiled floor, and he works through so that the artist can understand what's happening with the mathematics and then use it to make beautiful art. And it works in both ways as well, because mathematicians, now seeing these kind of rules for making these images that are projections of a scene onto a flat plane, in these images, you've kind of got parallel lines that meet in a strange way. I mean, they appear to meet. In the image, they meet. So it's potentially a different kind of geometry that we can explore, and this has grown into what we now call projective geometry, and there's loads and loads of fascinating things one could say about that on another day. But it's a brilliant, exciting development in mathematics that came about because of thinking of these things. Okay, so another example from art, and that is involving something that mathematicians are perhaps famed for liking to do, and that's counting. In particular, counting how many ways there are to make patterns, and here we're making patterns of shapes. We're making tilings of the plane. And tilings as a form of ornamental decorative art have been particularly prevalent in the Islamic world because of the traditional prohibition on representations of human beings, animals. So if you're not going to have a fresco with people sitting around eating grapes like you might have had in a Roman villa, what are you going to decorate your walls with? Well, maybe something like this, a beautiful repeating pattern, a periodic tiling of the plane. So, of course, if you're an artist making these things, your first question might be, well, what are my possibilities? What ways are there of fitting shapes together? And obviously there's lots of choice, different colours, you can tweak designs, so in some sense the answer's infinite, but in another sense it's very, very finite, because underlying any periodic tiling, like this one, a repeating pattern that could potentially go on forever in both directions, underneath every single one of those is one of just three basic fundamental, what are called regular tilings. So underneath this one, there's a pattern of equilateral triangles. A regular tiling is one where you have just one shape of tile, and it's got to be a regular polygon. So a polygon where all the sides are the same length and all the angles are the same. So equilateral triangle is one example. If you're going to do this with no gaps and no overlaps, then around each point, you've got to have a whole number of tiles. So if you think of it, you can do a little thought about the internal angles of regular polygons, and you can quickly work out that there are really only just three possibilities for these things. You can have 6 equilateral triangles, you can have 4 squares around a point, or you can have 3 regular hexagons. That's it, 3 possibilities. Then you have to think about how to colour these things and rotations and reflections and things, but still 3 underlying basic possibilities for regular tilings. Now, one artist who was very interested in possibilities here was MC Escher, and he was inspired by a visit to the Alhambra Palace, where that beautiful tiled wall I showed you is from, to start creating his own regular tilings, but of course without any restrictions on what he could represent. So very famously, Escher, did beautiful tilings with lizards, with birds flying in opposite directions, with fish, with little humans of various kinds, angels and devils was one. So he explored those ideas, but after some time, he felt, perhaps he's exhausted the possibilities. It was really only 3 underlying regular tilings. There are, even with all the variations, maybe he wanted something more. So, well, what else could we do? Well, a flat plane is not the only kind of geometric shape. We live on the surface of a sphere, and there's different possibilities there. It's a different kind of geometry. It's not the Euclidean geometry of the plane. On a sphere, it turns out there are 5 possible regular tilings. So how are we doing it? We're still doing it with tiles that are regular polygons. So the way to make one of these things is you make a regular polyhedron. In other words, one of these 5 guys, known as the Platonic solids. So you take, say, equilateral triangles, and you fit them together so that they make a closed shape. And there's 3 ways of doing it with equilateral triangles. Here's one that's my favourite one, the icosahedral form, where 5 equilateral triangles meet around each point. And so these, it turns out, are the only 5 regular polyhedra, and they give rise to 5 spherical tilings, because what you do, you take one of these things and essentially you inflate it so that it fits onto a sphere. That's being a bit lax there with the mathematics, but that's basically what happens. So there's 3 tilings of the plane. There's 5 of the sphere. That's only 8 still. What are we going to do? Well, luckily mathematics has an answer for us. There's a mathematician called Donald Coxeter who wanted to use a couple of Escher's pictures for a paper he was writing about symmetry. So Escher said, yes, you can. When the paper came out, Coxeter sent him a copy as a kind of a thank you. Escher wasn't sort of particularly interested in all of the complex mathematics and the equations that he could see, but he was very interested in one of the diagrams. This diagram. This is a different kind of tiling. It's obviously not quite, it's a different sort of thing than Escher had seen before. He was inspired by this and immediately set to work making his own. You can see the debt he owes to that picture on the left in this picture that Escher made. It is. It's what's known as a hyperbolic tiling. So what we're seeing here is a map of a different kind of geometry, hyperbolic space. And just like when we do a map of the world, you can't represent exactly without some distortion on a flat piece of paper the whole of a sphere. Something is going to get distorted. It's the same thing here. So if we had our hyperbolic eyes on instead of our boring Euclidean eyes, each of these triangles would look exactly the same. They are congruent triangles in that kind of geometry. What's happening is that towards the edge of that disk, the things aren't really getting smaller at all. They're just getting further away. And the edge of the disk you never actually reach because that's infinity. That's infinitely far away. So if we were hyperbolic beings, we'd be looking at this and seeing genuinely tiling of all of congruent triangles. Now, they're not regular, they're not equilateral triangles, even in the hyperbolic world, but underlying any tiling, just as we saw earlier for regular tilings of the plane, underneath any one of these, there is a regular tiling. In this case, it's a regular tiling where 4 regular hyperbolic hexagons meet at each point. And the great news for Escher is there were 3 tilings, regular tilings of the plane. There were 5 of the sphere. Guess how many there are for hyperbolic space? Infinitely many possibilities for Escher to own. So that's great news for the artist, because then he can just do so much to explore. He made lots more pictures like this, Escher. Here's, I think, my favorite one called Circle Limit 3. That's lovely. This one is based on an underlying tiling where you have 8 equilateral triangles meeting at a point. Nowadays, anyone can make these things because there are some brilliant tools online to do it. So I use Malin Christensen's free online tool to make this, which is a Gresham-based tiling where 4 regular pentagons are meeting at each point. So you can go and explore that, have fun with that. So we can all be artists to some extent now. So this is great, more ideas and more tools for artists to use and create. And for mathematicians as well, it leads us to think about what the possibilities are, and there's interesting mathematics to be done and discovered. So in the few minutes we have remaining, I want to briefly give you a couple of examples from the world of music, but also to flag that if you want to know lots and lots and lots more about wonderful interdisciplinary, multidisciplinary things connected with music, go to the Gresham YouTube channel and check out the Festival of Musical Ideas, which was held way back in the past on the 20th of June, 2025. So there'll be some maths and music there as well, along with lots of other things, but just to kind of give you a couple of other little examples to keep you going. And we'll see different things at the festival. There'll be 2 examples of where a musical problem question has led to some really interesting mathematics, especially in my field of algebra. And then we'll look at a different example where musicians have used concepts from mathematics to structure their composition. Okay, so the first example then, bell ringing. And this is something, we're in the centre of London here at Gresham College. Historically, bell ringing has been a really big deal in the city with societies of bell ringers almost competing to produce the most stupendous feats of ringing. And in England, there's a particular tradition of bell ringing called change ringing, which is where, due to the way that bells tend to be set up in churches here, you've got a different sort of challenge to meet when you want to make music with bells. So as the picture shows you, we have full circle ringing, which means when you set the bell going, it goes all the way around. And so here you might have 8 bells, each tuned to a different pitch from high to low, and then you all start them going with the ropes, right? And so they've got this momentum, they keep going, so you can't just sort of stop and start them. They are big, heavy things. Therefore, you can't just play a tune. You can't just say, I'll ring this one and then not ring it, and then I'll ring this one and it'll stop. They are all going round and round and round. So you've got some constraints here. So what you do then in change ringing is you have your set of bells, a ring of bells, and you ring them each in some order, and that's called a row. Okay, so you sound your bells in a sequence of rows, and in every row, every bell sounds exactly once, in some order. So, for example, if you had 3 bells, which wouldn't be very many, we can label them 1, 2, and 3 from highest to lowest. And if you work it out, you can find that there are 6 possible rows that you could ring. You go 1, then 2, then 3, or 1, then 3, then 2, and so on. So a challenge is, can I find a way to, let's do an interesting thing, and ring all possible rows? In this case, there'd be 6 rows. That's called an extent. So you do all the possible rows. And in fact, you always start with 1, 2, 3 down to the last one, n. Then you ring every other possible row exactly once and then finish up way back where you started. So that's what an extent is. So can we do this? That's the first question. Is this possible? I mean, it seems like it, yeah, just play all the rows, right? But there's a difficulty. The difficulty is, as I've mentioned, bells are heavy. And so you can't change the order too much. If you've got 8 bells and you played number 8 last, you can't in your next row suddenly play it first because it's still sort of going around and coming back to the beginning again. So the rule says every bell moves in the ordering at most one place. So if it was first, it can now be second, but it can't be ninth, right? So this is a constraint, a restriction. And all this you can see is so mathematical. It's brilliant. So the question is now, with this constraint, actually, can we even do this? Is this possible? Now, with 3 bells, if we just take the order that I've written the rows down in, can we go do 1, 2, 3, and then do 1, 3, 2? Yeah, that's fine, actually, because you just swapped 2 and 3 over. You just swapped an adjacent pair. So that's fine. But then the next number in that list, the next row in that list, as I've written it, was 2, 1, 3. Can we do that? No, that doesn't work, because 2 started at the end, it was at the end, and then we're asking it to move up to the beginning. We're asking it to move 2 positions. There isn't time to just finesse. You can finesse it a little bit, how long it takes to go all the way around. You can slightly pause at the top or make it come down a bit quicker, but you can't move 2 positions in one go. So that is not going to work. So what do we do? Well, we can try the only other possibility at that point, and it turns out if you do start with 1, 2, 3, then you swap the last 2, so you get 1, 3, 2, then you swap the first 2, 3, 1, 2, and then you swap the last 2, the first 2, the last 2. You alternate like that, actually it works, you get everything done. There is an extent on 3 bells. 3 bells isn't very many. Most bell towers have, probably 8, 6 or 7 or 8, but not more than 3. There are a lot of combinations when the number of bells starts going up. There's only 6 for 3 bells, but there's 24 for 4 bells, there's 120 for 5 bells, and 720 for 6 bells, and so on, right? So it's a lot. And just trial and error seems to be a bit of a dangerous approach to rely on. How, the number of ways of ordering that many rows is just crazy big. So question number 1, that's a mathematical question, really, is there an extent always? Is there always going to be something that works for n bells? Maybe n is 7. And there's another question. It turns out the answer is yes. We can prove that mathematically. The next question, though, is there an interesting extent? So what I mean by interesting is sonically interesting. That is, if you've got 8 bells, or let's say 7 bells, if you just from one row to the next only swap one pair, then it sounds really similar to what you just heard. It's boring. What you want to do is make the most change between rows. So the most things you can do with 7 bells is you're swapping pairs over, right? There are 3 pairs plus 1 left over in 7. So the best you can do if you have 7 bells is do like a triple swap. That would be great. Could we do an extent that only has triple swaps? This question was raised by someone quite local to Gresham, Fabian Stedman. And the picture I'm showing you there is a lovely bell-shaped plaque in his honour at the Church St Andrew's Undershaft, which you should go and have a look at if you're passing. He did a great deal in the 17th century to really set in train the art of change ringing, of bell ringing, and the traditions that evolved. And he wrote a couple of books about it and really popularized some of the standard techniques. Lots of things are named after him. And he made this claim, conjecture, we would now call it, that you can do an extent on 7 bells containing only these triple swaps. It took a long time for mathematicians to prove this. It can be done. No one knew if it was true or not. It can be done. It was solved in 1994. It took a long time. It's fantastic. There are still lots of open questions in mathematics of bell ringing. So if you want to, do a PhD in mathematics, and you want to study bell ringing, this is a hot topic. So yeah, very cool, and it's led to some really interesting mathematics. It's all algebra. It's all group theory, which is my thing, which I like. So we're going to finish up then with a final example, and this is of how musicians, composers can use structures and ideas from mathematics as a framework for composition. Now, this is not a kind of really dull thing where you slavishly obey a formal structure. These things are tools. They are frameworks that inspire creativity. It's like, you can write a brilliant sonnet, even though a sonnet must have 14 lines and must have a particular rhyme scheme. That doesn't stop you writing a good poem. It spurs your creativity to fit within that structure. And so for always, artists, musicians have used these kind of frameworks, whether it's variations on a theme or being inspired by a particular poem. And mathematical structures can act as these frameworks too. So here's an example of a mathematical structure. This is a fractal, one of probably the most famous fractal that there is. It's the Mandelbrot set. And it exhibits one of the key qualities of fractals, which is self-similarity. So if we all mesmerize ourselves by watching this, you see the original design is shown at smaller and smaller scales. It keeps reappearing. You keep seeing that sort of beetle-like image coming back. There it is coming up to us. We'll just see that, and then we'll go back so we don't. There we go. There it is. OK, so you see the same design at smaller and smaller scales. It's called self-similarity. And some composers have used fractals in their composition, but not fractals like this image, fractal sequences. So Kaija Saariaho is one example of this, a Finnish composer. She used fractal sequences in this composition, Jardin Secret. And so you might be thinking, what's a fractal sequence? Right? We might have seen an image. What's a fractal sequence? Well, I'll give you an example of one. It's not this yet. So these are just the numbers 1, 2, 3, 4, 5, and so on, written in binary. But then what you do is you make a sequence from them by writing down how many ones there are in each term. So there's 1, another 1, and then there's 2 ones, and then 1 again, 2, 2, 3, 1, 2, and so on. You can carry on. So that's the sequence. Now, it's a fractal sequence. And the reason I say that is because it contains itself many times. If you look at just alternating terms, I'm going to highlight them like that in green, pull those out and have a look. It's exactly the same sequence being produced. So every other term of that sequence is the sequence. And you can do that again and again, infinitely many times. There are infinitely many copies of this sequence contained within itself. So that's the self-similarity again. It's really lovely. And if you use this in composition, what you find is you get a real richness of structure because you get echoes and shorter versions and longer versions and augmented and diminished versions of the melody that you kind of pick up echoes of at smaller and larger scales throughout the piece of music. So it's a really lovely thing. I'm going to finish with, because I'm soppy, with a quote from Longfellow. He wrote a little book called Cavanna, which isn't very well known, but it's about, it has a character who's a teacher, and he's having a conversation with his wife about mathematics, and he says this lovely thing that mathematics holds the sea in the hollow of its hand. It measures the earth, it weighs the stars, it illumines the universe. It is law, it is order, it is beauty, and that's wonderful. But then he goes on to say, but we just think it's about bookkeeping. Right? People don't know. Oh dear. So then he takes down a little book to show his wife. Little old book. Here's an old book of mathematics. It's quite different. What is it, she says? It's the Lillivati. So that's quite nice. And yeah, because it's full of poetry and it's charming. And for me, he says that we teach it in a way that makes mathematics feel prosaic. Well, teachers, I have nothing but admiration for teachers at all levels. They do amazingly well at keeping their subjects exciting in spite of ever-changing diktats from on high about what must be packed into the syllabus this year. But in a healthy society, learning doesn't stop with school. It doesn't stop even with university. We have to cherish and feed our curiosity. And that's where Gresham College comes in. As the provost, I have to say this. But genuinely, this is how I feel. Gresham College is a chance to go beyond, to explore ideas, to feed your curiosity without being bound by the strictures of a defined subject curriculum. And for over 400 years, Gresham has been a place, a haven for people to come and hear exciting ideas and to be challenged and to think, and that's so important. So for me, I'm really honoured to have given this Provost lecture, and I encourage you all to explore everything we have at Gresham, our online archive. Come to our in-person lectures, come and say hello and spread the word about this precious institution. Thank you.